Hello everyone, I am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss some analytical problems based on the concepts of light emitting diode, Zener diode and photodiode. So before seeing the problems, let us recollect all the formulae that we are going to use to solve the numerical problems. So the first one is Eg is equal to Hc by lambda. Eg here represents the energy emitted or it is nothing but the energy gap. It is nothing but the energy gap. Then H here is the Planck's constant. H is the Planck's constant whose value is 6.625 into 10 power minus 34 joule seconds. This is the value of H. And C here represents the velocity of light. Whose value we all know, 3 into 10 power 8 meters per second. And lambda here is the wavelength. Wavelength of light that is emitted. Okay. So if you know the value of lambda, we can easily find the energy that is emitted, which is equal to the energy gap, because H and C are constants. And in some cases, they give us the value of the energy gap and ask us to find lambda. So using the same formula, just by transposing, we can write the formula as lambda is equal to Hc by Eg. So lambda is equal to Hc by Eg. So most of the times you get numericals or analytical problems to find the value of Eg, the energy gap or the energy emitted, or the wavelength. So we'll be using these two formula most of the time. And then here one concept what we need to understand is, whenever we are talking about the energy band diagram, this is the valence band. That is, the energies possessed by all the valence electrons put together will form a band, and we are calling it as valence band, and the topmost level here is EV. And this is the conduction band. Conduction band is the range of energies possessed by all the free electrons. So free electrons are conduction electrons. So we call them as free electrons or conduction electrons. So these are the range of energies possessed by conduction electrons, and the lowest level is represented by EC. Now, in a light emitting diode, whenever an electron that is there in the conduction band recombines with the hole in the valence band, this is the electron here I can say, and this is the hole. When it recombines, the energy is being emitted, and this is equal to h nu. So how we are getting this formula? E is equal to h nu, and nu is nothing but C by lambda. So E is equal to h nu, that is equal to hc by lambda. So what will be the difference in energy that is emitted is always equal to the energy gap, Eg. That is what we have to understand before doing the numericals. So the first one we are going to do is calculate the wavelength of the emitted radiation from an LED made up of gallium arsenide with a band gap of 1.52 electron volt. So what is given here is, first we'll write the given data. What is the data that is given? We are given the band gap. So I'll write the band gap as Eg is equal to 1.52 electron volt. And what we have to find, calculate what? Wavelength. So lambda is equal to how much? So what is the formula we are going to use to calculate lambda here? Lambda is equal to Hc upon Eg. Lambda is equal to Hc upon Eg. So H and C are constants. H is how much? 6.625 into 10 power minus 34 joule seconds. C is the velocity of light. It is 3 into 10 power 8 meter per second. And Eg is given in electron volt, and we have to convert it into joules because all the units are in SI system. So the energy has to be expressed in joules in the SI system. In SI system, energy is expressed in joules. So we are going to convert this 1.52 electron volt into joules. So what is the conversion? 1 electron volt is equal to 1.6 into 10 power minus 19 joules. This is the conversion from electron volt to joules. So now Eg will be equal to 1.52 into 1.6 into 10 power minus 19. This will be in joules. So we have H, C and Eg. It is now direct substitution to get lambda. So lambda is equal to 6.625 into 10 power minus 34 into C, that is 3 into 10 power 8 upon, we have tried Eg in joules. So 1.52 into 1.6 into 10 power minus 19. So you can use your calculator, the scientific calculator, to simplify this, and we get the value of lambda as 8.17 into 10 power minus 7 meters. 8.17 into 10 power minus 7 meters. And the value of lambda is generally expressed in angstrom. So we can convert it into angstroms also. So I can write the same thing as 8170. Means I'm shifting the decimal place to 3 points onto the right. So we get 10 power minus 10 meter. And what is 1 angstrom equal to? 10 power minus 10 meter. So I can simply write this as 8170 angstroms. So the wavelength of the emitted radiation is 8170 angstroms. Now coming to the second one, a semiconductor diode laser has a wavelength of 1.65 micrometer. The wavelength is given here. Wavelength is how much? 1.65 micrometer. We have to find the band gap in electron volt. We have to express the band gap in electron volt. So let us write the data given. Lambda is given 1.65 micrometer. We have to find Eg. H is constant. 6.625 into 10 power minus 34 joule second. C is also constant. 3 into 10 power 8 meter per second. And we have to convert this micrometer to meter because all have to be in the SI system. So this will be 1.65 into 10 power minus 6 meter. Micro means 10 power minus 6. So what is the formula we are going to use here? Eg is equal to hc by lambda. So just to substitute the values of hc and lambda. 6.625 into 10 power minus 34 into 3 into 10 power 8, that is C, upon lambda. We have converted it into meter. So 1.65 into 10 power minus 6. So hc by lambda. So we are going to get the value of energy in joules because in SI system we get it in joules. So the value we get when you use the scientific calculator and simplify it, you get 12.04 into 10 power minus 20 joules. This is in joules. But in the question, it is asked that we have to express the band gap in electron volt. So what is the conversion we have seen? 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So how do we convert this joules to electron volt? We'll just divide it with 1.6 into 10 power minus 19. So 12.04 into 10 power minus 20 divided by 1.6 into 10 power minus 19. So what we get here is 0.75 electron volt. So the band gap or the energy gap expressed in electron volt is 0.75. Now let us see the third one. Determine the wavelength of light emitted from LED, which is made up of gallium arsenic phosphide semiconductor, whose forbidden energy gap is 1.875 electron volt. The energy gap is given here. Forbidden gap or forbidden energy gap mean the energy gap EG. Then mention the color of the light emitted. So what we have to find here, determine the wavelength. Once we calculate the wavelength, depending upon the wavelength, we can tell the color of the light that is emitted. So let us write the data. The data here given is energy gap. EG is given. EG is 1.875 electron volt. And we have to calculate the wavelength of light. Lambda we have to calculate. So what is the formula we are going to use? Lambda is equal to Hc upon Eg. H is equal to 6.625 into 10 power minus 34 joule seconds, and C is equal to 3 into 10 power 8 meter per second. And we have to convert this electron volts into joules. 1.875 into 1.6 into 10 power minus 19 joules. So we have got all the values. We have Eg, we have H, we have C. Now it is simply substitution. So lambda will be equal to Hc 6.625 into 10 power minus 34 into 3 into 10 power 8. This is H and this is C. Now we have to write the value of energy gap that is converted into joules. That is 1.875 into 1.6 into 10 power minus 19. So we get the value of lambda. So when you simplify this using a calculator, we have 6.625 into 10 power minus 7 meter. Or if we convert this into angstrom, I can express the value of lambda in angstrom. In the previous problem also we have seen, I can write lambda as 6625 into 10 power minus 10 meter. How I am doing this conversion is, I have just shifted the decimal place to 3 points, so I get 10 into 10 power minus 3. So 10 power minus 7 and 10 power minus 3 gives us 10 power minus 10. Because 1 angstrom is equal to 10 power minus 10 meter, I can simply write it as 6625 angstrom. So the first part in the problem is to calculate the wavelength of light. We have calculated the wavelength is 6625 angstrom. Now the next step is to mention the color of the light. So how do we mention the color of the light? If you see the visible light with GR, whatever light that is visible to a normal human eye, we say, it ranges from 4000 approximately 4000 to 6600 angstroms, or sometimes they say 7000 angstrom. So this is in the region of red. So we say that the light that is emitted is red in color. So light emitted will be red in color. So depending upon the wavelength, we will be able to identify the color of the light. So it is red in color. Next, we'll see a numerical based on Zener diode. Till now, we have seen numericals based on light emitting diode. So this is on Zener diode. Find the current through the Zener diode when the load resistance is 2 kilo ohms. So this is the circuit we have. This is input voltage, input 15 volts, and then we have a load resistance given, RL is equal to 2 kilo ohms. This is kilo ohm. And here the resistance to regulate the current is 1 kilo ohm. We have the Zener diode. This is the Zener diode symbol used, and the voltage across it is 9 volt. So what we have to find here is the current through the Zener diode we have to find, and we are given the load resistance RL. So RL is equal to 2 kilo ohm. We have to find the current through the Zener diode. So how do we calculate the current through the Zener diode? First, what we do is we will find out the current that is flowing through this resistor R. So this is the total current I. And then we will also find the current that is flowing through the load resistance. We can say this is IL. So the difference between I and IL gives us the current that is flowing through the Zener diode, IZ. That is how we are going to calculate. First find I and then find IL. So I minus IL gives us IZ, that is the current flowing through the Zener diode. So what is the formula we are going to use to calculate the current? It is our basic formula, that is the Ohm's law formula we are going to use. We know V upon I is equal to R. or if I have to find the current I, it will be equal to V upon R. So first let us find the current I flowing through this RZ. So I will be equal to V upon RZ. Now the point here is, what is the voltage across this resistance? Here it is 15 volts and here it is 9 volt. So voltage across RZ will be V, that is 15 minus 9, that is 6 volt. 6 volt is the voltage. So we can calculate the total current now. 6 upon, what is the resistance? 1 kilo ohm. So what is 1 kilo ohm equal to? 1 into 10 power 3. Kilo is 10 power 3. So I can write it as 6 into 10 power minus 3 ampere, or simply we can write it as 6 milliampere. So the current flowing through this resistance is 6 milliampere. Now the next thing is, we have to calculate the current flowing through the load. So what is the voltage across this load resistor is 9. So we can calculate IL, that is the current flowing through the load will be voltage across the load upon the resistance. So the voltage across the load is the same voltage across the Zener diode. So it is 9 by RL. What is RL? 2 kilo ohms. So 2 into 10 power 3. Kilo is 10 power 3. So 9 by 2 is 4.5 into 10 power minus 3 ampere. 10 power 3, if it comes to the numerator, it is 10 power minus 3. So I can simply write this as 4.5 milliampere. So the current flowing through this resistor is 6 milliampere and the current flowing through the load resistor is 4.5. So the current flowing through Z, that is the Zener diode IZ, will be I minus IL. So this is 6 minus 4.5, that will be 1.5 milliampere. So that is how, when we are using a Zener diode, when excess current flows through the circuit, so the output can be maintained constant. Next question is, for what voltage will the reverse current in PN junction diode reach 90% of its saturation value at room temperature? What we have to find here is the voltage. What is given is the current is 90% of the saturation value and the temperature is room temperature. So let us write the data first. What is the data given? I is equal to 90% of the saturation current. I is 90% of IS. And the temperature here is room temperature. We can take it as 27 degrees Celsius. That will be equal to 300 Kelvin. We will convert it into Kelvin. So 300 Kelvin. We have to find V. V is equal to how much? And the ideality factor is not given, so we can take the ideality factor as 1. So what is the formula we have for the current? I is equal to IS exponential EV by beta KT minus 1. So this is the formula we have. We are not given I and IS separately. We are given the relationship between I and IS. So it is 90% of IS, means I can write 90 by 100 IS, or this is nothing but 0.9 IS. I is equal to 0.9 IS. So let us do the substitution in the formula. I'll write the formula as I upon IS is equal to exponential EV by beta KT minus 1. Now what is I upon IS? I is equal to 0.9 IS. And also one more thing we have to remember here, it is reverse current. So we will write it as minus. So minus 0.9 IS by IS is equal to exponential. Let us substitute the values for E, V, beta, KT. E is the charge, 1.6 into 10 power minus 19 into V, we have to find, upon beta KT. Beta is what? 1. K is 1.38 into 10 power minus 23 into the temperature here given is 300 Kelvin minus 1. So IS and IS will get cancelled. I can bring minus 1 onto this side. So 1 minus 0.9 is equal to exponential, the same value we get here. So 1 minus 0.9 is 0.1. So what we do here is we will take logarithm on both sides. 0.1 is equal to exponential, the same value, taking logarithm on both the sides. Taking log on both sides. What we have is ln 0.1 will be equal to, this exponential and ln will cancel. We have just 1.6 into 10 power minus 19 into V upon 1.38 into 10 power minus 23 into 300. So now we will just transpose, we will consider the value of ln 0.1 and find the value of V. So V will be equal to what? The value of ln 0.1 is minus 2.3 into 1.38 into 10 power minus 23 into 300 divided by 1.6 into 10 power minus 19. So we get the voltage to be minus 0.06 volts. So this is the voltage at which the current will become 90% of its saturation value at room temperature. Now coming to the sixth one, a particular green LED emits light of wavelength 5490 angstrom. Find the energy gap of the semiconductor material. So we are having a green color LED and it is emitting light of wavelength 5490. We have to calculate the energy band gap. We have done similar problems before. So write the data first. Wavelength lambda is 5490 angstroms. You have to find Eg, the energy gap. The formula we are going to use here is Eg is equal to Hc by lambda. H and C are constants. We will convert this wavelength into meters. So what is the conversion? 1 angstrom is 10 power minus 10 meters. 1 angstrom is equal to 10 power minus 10 meters. So the wavelength now will be 5490 into 10 power minus 10 meter. So substitute in Eg is equal to the value of H 6.625 into 10 power minus 34 into the value of C, Hc 3 into 10 power 8 upon lambda we have converted it into meters. 5490 into 10 power minus 10 meters. Okay, I need not write meters here. We are doing the simplification. So simplify using the calci. You get EZ is equal to 3.62 into 10 power minus 19 joules. So in SI system, the energy is obtained in joules. If we have to convert this into electron volt, what we do? We use the conversion. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So divide this value 3.62 into 10 power minus 19, we are going to divide with 1.6 into 10 power minus 19. So we get 2.26. This will be in electron volt. So what is the energy gap we are getting here? Is 2.26 electron volt. Now coming to the seventh one. In a germanium diode, if the reverse saturation current is 10 microamperes at room temperature, calculate the forward current for a voltage of 0.2 volts. So what we have to write first is the data. Saturation current is 10 microampere. So we write IS is equal to 10 microampere and the voltage given is 0.2 volts and the temperature is room temperature. We take it as 27 degrees Celsius. What we have to calculate is current. I is equal to how much? So first let us do the conversions. 10 into 10 power minus 6 ampere. Micro is what? 10 power minus 6. And the temperature also will express it in Kelvin. So this will be 27 plus 273. That is 300 Kelvin. So we have the current, saturation current, 10 into 10 power minus 6 ampere, or we can straight away write it as 10 power minus 5 ampere, and the temperature is 300 Kelvin. Now we'll write the formula and do the substitution. So what is the formula we have? I is equal to IS exponential EV by beta KT minus 1. And beta is not given here, so we consider it as 1. And for germanium, generally, the value of beta, which is the ideality factor, we say, it is equal to 1. So let us substitute the values. So I is equal to, I can write it as 10 power minus 5 exponential. E is the charge of the electron, 1.6 into 10 power minus 19. And the voltage given is 0.2 volts divided by 1, beta value is 1, into K is 1.38 into 10 power minus 23 into the temperature here is 300 minus 1. So what we have to first do is find the value of the exponential. Whatever is there in the bracket, we try to find out its value. So it is exponential 7.73 minus 1. So simplify the thing in the bracket, we get 7.73. Now you can use the calci and find the exponential value of 7.73, and that comes out to be 2275.6 minus 1. So I will be equal to what? 2275.6 will be 2274.6 into 10 power minus 5. And if we have to write it in the standard form, we will write it as 2.2746, We have shifted it 3 decimal places, so it will be 10 power minus 2 ampere. So the current flowing will be 2.2746 into 10 power minus 2 ampere. The next one is calculate the thermal voltage when the temperature is 25 degrees Celsius. This is a very simple problem, but wherever we are given the thermal voltage or we have to calculate the thermal voltage, this becomes very handy. We have to calculate the thermal voltage and the temperature is given. So the data given here is just the temperature. T is equal to 25 degrees Celsius. We have to convert this temperature into Kelvin. So 25 plus 273. So that will be 298 Kelvin. So the temperature is 298 Kelvin. What we have to calculate is the thermal voltage Vt. So what is the formula for Vt? Formula for Vt is kT by E. Vt is equal to kT by E, where k is the Boltzmann constant. K value is 1.38 into 10 power minus 23 joule per Kelvin, and E is 1.6 into 10 to the power of minus 19 coulombs. So we will write the value of Vt now. Find Vt is equal to 1.38 into 10 power minus 23 into the temperature 298 Kelvin upon 1.6 into 10 power minus 19. So we get the voltage as 0.0257 volts. So this is the value of the thermal voltage. Now coming to the next one. What is the ratio of current for a forward bias of 0.05 volt to the current for the same magnitude of reverse bias? If it is forward bias, it is 0.05 volt and the magnitude is the same, and the reverse bias, we have to find the current at room temperature. And this is for a germanium diode. So let us first write the data. We will write in forward bias first we will write. Forward bias, we have I is equal to I1 and IS is equal to IS1 and V is equal to V1, which is given as 0.05 volt, and the temperature given is room temperature. So we will take it as 27 degrees Celsius, which is 300 Kelvin, and it is a germanium diode, so beta is equal to 1. This is the case for forward bias. Now what it will be for reverse bias? What do we take? I is equal to I2, IS is equal to IS2, and the voltage is V2, which is minus 0.05 volt, because it is in reverse bias. Magnitude is the same, but it is in reverse bias. So we have taken minus 0.05 volt, and the temperature is the same, room temperature 300 Kelvin, and beta is equal to 1. So what we have to find here is the ratio of the current I1 by I2. This is what we have to find. I1 by I2 is equal to what? And one more thing what we have to understand is IS1 will be equal to IS2. This is also there. IS1 is equal to IS2. So let us write the formula. We will write it in terms of Vt, Is into exponential V by beta Vt, because we have seen Vt is equal to Kt by E. Just now we have done the numerical based on this formula. So EV will become beta Vt, and since beta is equal to 1, I can simply write it as exponential V by Vt minus 1. So we have just simplified the formula, substituting the values. Now I1 by I2 will be equal to IS1 by IS2, which are equal, and finally they get cancelled. This will be exponential. What is the value here we have for V is 0.05 by Vt. We can find the value of Vt and keep it ready. What is Vt? It is Kt by E. K is 1.38 into 10 power minus 23 into T, and E is also constant, 1.6 into 10 power minus 19. So we get the value of Vt to be T by 11600. This value we can always directly use the value because K and E are constants. So we can substitute that value here in Vt. So I'll write it as 11600 upon T, that is 300, minus 1 divided by exponential minus 0.05 into 11600 upon 300 minus 1. So here IS1 and IS2 are equal, I said. They get cancelled. So we will find the exponential value and minus 1. So what we are going to do is I1 by I2, simplifying the numerator and denominator using the calculator. The numerator comes out to be 5.91 and the denominator is negative value. It is minus 0.86. So the ratio will be minus 6.87. Since it is a ratio, it does not have any units. So the ratio here we are getting I1 by I2 as minus 6.87. So we will stop here. For more numericals on these topics, you can refer to this link given in number 4 and solve more numericals, and you can also refer to these textbooks for clearing the concepts regarding the LEDs and Zener diodes and photodiodes. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.